If you stand outside on a clear night and look toward the constellation Centaurus, you're looking in the direction of the closest star to our Sun. It's there. It has been there for billions of years, and yet no human being will ever see it up close. That feels strange. We've walked on the moon. We've sent spacecraft beyond the edge of the solar system. We can land robots on Mars with astonishing precision. So why does the next star remain unreachable? Is it simply a matter of building a faster rocket? Or is something deeper stopping us? To understand why the nearest star is forever out of reach, we have to begin with something most people underestimate: distance. Proxima Centauri, the closest known star beyond our Sun, is about 4.24 light-years away. A light-year is not a measure of time. It is the distance light travels in 1 year. Light moves at about 300,000 kilometers per second. In 1 year, that adds up to nearly 9.5 trillion kilometers. Multiply that by 4.24, and you arrive at roughly 40 trillion kilometers. Numbers that large tend to slip past the mind, so it helps to shrink the scale. Imagine the Earth reduced to the size of a marble. On that scale, the Sun would sit about 30 meters away, roughly the length of a swimming pool. That already feels spacious. But Proxima Centauri would not be a little farther down the field. It would be thousands of kilometers away, an empty gap stretching across continents. That is the canyon between stars. Within our solar system, distances feel manageable. The Moon is about 384,000 kilometers away. Apollo astronauts reached it in 3 days. Even the Sun, at 150 million kilometers, is only 8 light minutes away. In cosmic terms, that is still local. But once you step beyond the outer planets, the scale changes completely. The space between stars is not just large, it is almost unimaginably large. So how fast can we travel? The fastest object humanity has ever built is NASA's Parker Solar Probe. At its peak, it travels about 700,000 kilometers per hour. That is fast enough to cross the United States in seconds. It is faster than any spacecraft before it, and it is nowhere near fast enough. At that speed, reaching Proxima Centauri would take more than 6,000 years. When that journey began, human civilization would have looked entirely different. When it ended, if it ever did, humanity itself might no longer exist. And even that calculation is generous. The Parker Solar Probe achieves its speed by falling toward the Sun, using gravity to accelerate. A spacecraft traveling outward, away from the Sun and toward another star, would not benefit from that same boost. Perhaps then, the solution is simply to build something faster. That is where physics steps in. There is a formula in aerospace engineering called the Tsiolkovsky rocket equation. It describes how rockets gain speed by expelling mass. The more speed you want, the more fuel you need. But fuel has mass, and mass requires more fuel to accelerate. Which adds more mass? Which requires more fuel? The relationship is exponential, not linear, exponential. To accelerate even a modest spacecraft to 10% of the speed of light using traditional chemical rockets would require more fuel than exists on Earth. Not more fuel than we can carry. More fuel than the planet itself can provide. This is not a funding problem. It is not an engineering oversight. It is a structural feature of how rockets work. Engineers have explored alternatives. Ion thrusters, for example, use electric fields to accelerate charged particles. The thrust is gentle, almost delicate, but it can operate continuously for years. NASA's Dawn spacecraft successfully used ion propulsion to travel between asteroids. Nuclear thermal propulsion could, in theory, double the efficiency of chemical rockets by using a nuclear reactor to heat hydrogen propellant. More ambitious concepts, like nuclear pulse propulsion, would detonate small nuclear explosions behind a spacecraft to push it forward. On paper, some of these ideas could reach a few percent of the speed of light. But even at 5% of light speed, the journey to Proxima Centauri would take roughly 85 years. At 10%, about 43 years. That is faster than thousands of years, but still an entire human lifetime. And none of these systems currently exist in operational form for interstellar travel. They remain concepts, studies, and prototypes. Even if propulsion were solved, another barrier remains: the speed of light itself. According to Einstein's theory of special relativity, as an object with mass accelerates toward the speed of light, the energy required to push it further increases dramatically. Closer and closer to light speed, the energy requirement grows without bound. Not extremely large, infinite. No amount of engineering can bypass that limit. It is woven into the structure of space and time. Light speed is not a technological hurdle. It is a fundamental ceiling. This means that even in the most optimistic scenario, interstellar travel would always take decades at a minimum. No shortcut through conventional physics allows a human-carrying spacecraft to cross light years in days or weeks. And then there is the journey itself. Space between stars is not truly empty. It contains sparse particles, dust, and radiation. At 10 or 20% of the speed, even a tiny grain of dust would strike with enormous energy. What seems insignificant at low speed becomes catastrophic at relativistic speeds. Shielding against such impacts would add more mass. More mass requires more energy. The same old cycle returns. Radiation poses another threat. Beyond Earth's magnetic field, astronauts are exposed to cosmic rays and high-energy particles. On the International Space Station, which still benefits partially from Earth's protection, astronauts receive significantly more radiation than on the ground. In deep interstellar space, shielding would need to be substantial, but dense shielding materials can create secondary radiation when struck by high-energy particles, complicating protection further. Over decades, cumulative radiation exposure could damage DNA, increase cancer risk, and impair cognitive function. The human body presents its own limitations. In microgravity, bones lose density, muscles weaken, the cardiovascular system changes. Astronauts on the International Space Station exercise for hours each day to slow these effects, yet some changes persist even after returning to Earth. On a journey lasting 40 years or more, artificial gravity would likely be necessary. This would require rotating habitats large enough to create meaningful centrifugal force. Designing such a structure to survive acceleration, radiation, and potential impacts adds layers of complexity, and beyond the physical challenges lies the psychological ones. A message sent from Proxima Centauri would take 4.24 years to reach Earth. A reply would take another 4.24 years to return. Communication delays alone would isolate a crew profoundly. No real-time conversations, no immediate assistance, no connection to unfolding events at home. Long-duration isolation studies on Earth consistently show rising stress, conflict, and cognitive strain over time. On an interstellar voyage, there would be no option to return, no rescue mission. Some have proposed generation ships where multiple generations live and die aboard a spacecraft, with descendants eventually arriving at their destination. But human societies evolve quickly. Languages shift. Cultural values change. Maintaining a unified mission over centuries may be as difficult as the engineering itself. There are theoretical ideas that attempt to bypass these problems entirely. Wormholes, if they exist, could act as shortcuts through spacetime. Warp drive concepts suggest bending space itself so that a spacecraft remains stationary while space moves around it. These ideas emerge from legitimate mathematical solutions in general relativity. But translating mathematics into engineering requires conditions we have never observed, such as exotic matter with negative energy density. Some warp drive calculations demand energy equivalent to the mass of entire planets. For now, they remain theoretical possibilities, not technologies waiting in a laboratory. So where does that leave us? It leaves us standing at the edge of an immense cosmic distance, aware of what lies beyond, but constrained by the laws that govern reality. The nearest star is not unreachable because of a temporary technological gap. It is unreachable because the universe is vast, energy is finite, and the speed of light is absolute. And yet, there is something remarkable in that realization. Even if we never physically cross the gap, we can still study it. Telescopes such as the James Webb Space Telescope can analyze light from distant star systems, searching for chemical signatures in alien atmospheres. We can detect planets we will never visit. We can measure distances we will never travel. Our rockets may be limited, but our understanding is not. Perhaps the deeper story is not about failure. It is about scale. The universe is built on distances so large that even our greatest achievements remain local. The solar system, vast as it seems, is only a small neighborhood. The stars will continue to shine whether we reach them or not. And maybe the most extraordinary thing is that from one small planet, orbiting one ordinary star, we have learned enough to know exactly why we cannot yet go farther. Thank you for watching. If you have another everyday mystery you'd like explored, let me know in the comments. And if you found this thoughtful or illuminating, consider liking the video and subscribing. It helps this channel continue asking and answering questions like this.